Hello, I am recording an intro video for chemical bonding. This video will provide an introduction to chemical bonding on that axis of ionic to covalent types of bonding, and then we'll go straight into Lewis structures and molecular geometries. So a chemical bond is the force that holds atoms together or ions together in a compound. Compounds are either molecules, which are covalently bonded, or they are ionic compounds that are held together by the charge attraction. So an ionic compound consists of two charged particles, a metal cation with a non-metal anion. A molecule is a compound that consists of nonmetals with nonmetals, such as water and carbon dioxide. We'll take a look first at ionic compounds and the transfer of electrons. So we saw most recently that elements tend to gain or lose electrons so that they have the same number of electrons as a noble gas. So completing that outermost shell, and that's known as the octet rule. Metal atoms typically lose electrons from their valence shell, so they become positively charged. Nonmetals typically gain electrons, and those add into the valence shell, completing it. Negatively charged particles are called anions. So we'll just review a little bit of what we learned with these diagrams right here. For sodium, sodium is number 11 on the periodic table. So it has 11 protons. And for the neutral atom, sodium would have 11 electrons out in their outer orbits. Now when that undergoes a change, and it loses an electron, well, it's still a sodium, so it's got 11 protons in the nucleus, but now it's lost an electron, so it has only 10 electrons in its outer shell. So I'm going to write that below as if it's a chemical equation. Sodium going to a sodium plus, well, that must have had one electron that got released. The reactants are sodium, and the products are sodium plus ion with one electron that got released. Let's take a look at sulfur. Sulfur is number 16, so it has 16 protons in the nucleus, and for the neutral atom, it has 16 electrons. If we look at the ion that it forms, sulfide ion, S2-, that's still sulfur, so it's got 16 protons in the nucleus, but now it has added 2 electrons. So it has a total of 18 valence electrons in its outer shells. If we want to write this as a chemical equation, which side are the electrons on? We want to look at the overall charge balance of products and reactants. The products have an overall charge of -2. So we know that the electrons will have to go on the reactant side of the equation. All right, when we look at those ions, sodium has become isoelectronic. So iso means same, and electronic is a number of electrons. So sodium has become isoelectronic with neon. It lost one electron, so it ended up with 10, and that is the same number as neon. Looking at sulfur, it gained 2 electrons, so that is like moving to the right by 2 boxes on the periodic table, and it becomes isoelectronic with argon. So circle all of the following ions that are isoelectronic with argon. For those not isoelectronic with argon, write the noble gas they are isoelectronic with. And you can pause the video for a minute to write these down and figure it out, and then continue. Potassium is in N equals 4, row 4. It's going to lose that 4s electron, and it will go back to look like the previous noble gas, which is argon. So I'll circle it. Strontium is in N equals 1, 2, 3, 4, 5. It's going to lose 2 of its electrons and look like krypton. Sometimes we use square brackets to show that it's a core. All right, aluminum is in n equals 3 and group 3, it loses all of its valence electrons, so it becomes isoelectronic with neon. Phosphorus is also in row 3. It's going to gain 3 electrons to take on that negative charge, so it becomes isoelectronic with argon. We'll find titanium. It's in the transition metals, in the top row of the transition metals, and it is losing 4 valence electrons, so we will count those boxes back. 1, 2, 3, 4, going back to the previous noble gas, and that is also isoelectronic with argon. Calcium. Calcium is N equals 4. It loses 2 valence electrons. It is also isoelectronic with argon. Oxygen gains 2 electrons, so that moves 2 boxes to the right to become isoelectronic with neon. And finally, magnesium. N equals 3. It loses those 3s electrons and becomes isoelectronic with neon. So we drew some Lewis structures right at the end last time. I'm going to do a quick review, and we will draw those Lewis structures for the neutral atom. So we'll write down the symbols for the element, Na. Sodium is in group 1, so it has 1 valence electron. So that is the Lewis structure for the neutral sodium. Magnesium is in group 2, and it has 2 electrons, and they take different sides of the atom. Let's take a look at chlorine. It's number 17. It's in group 7. 1, 2, 3, 4, 5, 6, 7. So you can see chlorine has 3 pairs and 1 unpaired electron. Finally, oxygen, 1, 2, 3, 4, 5, 6. And you can show those pairs on any of the sides. Right? We could equivalently write it like this. That would be equally correct. As long as we show 1 electron on all 4 sides first, and then go back and pair. All right. So let's take a look at what happens when it forms the ion. So we're going to form the ion. What happens to sodium? You can find it on the periodic table, and that might help. So when we have that sodium ion, it's going to lose that electron and show sodium plus. Magnesium is going to lose 2 electrons and form Mg plus 2. Oh, I'm going to write the 2 in front. I think that's how Bishop does it. So it loses its valence electrons, and that means that no electrons show in the Lewis structure. All right, for chlorine, let's find out on the periodic table. It's right next to argon, so we can see from its location on the periodic table that it will want to gain an electron. So we will write it with a -1 charge, and 1, 2, 3, 4, 5, 6, 7 from the original, and now it gained 1. So you can see easily that the octet rule is fulfilled. It's got 8 electrons around it. With oxygen, it's in group 6. It's going to gain 2 electrons to form an overall charge of 2-, and it too completes the octet rule. So let's take a look at some reactions, ions. Let's draw that sodium atom, and I'm going to draw my chlorine with the unpaired electron pointing towards sodium just to make it look easy. Right? We can draw it however we want. Those are going to form, react to form. There's our arrow. Now we have our sodium. We often put our ions in brackets, but I am not sure if that instruction is included here. I think we get to that a little later. So I'm going to put that in brackets because it has the charge with it. And what that shows, for example, with the chlorine, is that all of these electrons are on the chlorine, and they together carry the negative charge. So that helps us visualize what ionic compounds look like. It looks more like an exchange of the electron, where the sodium gave up its electron and the chlorine stole it from sodium. All right, let's take a look at magnesium and oxygen. So again, magnesium is going to form magnesium ion, and it will be attracted strongly to an oxide ion, and now both of them have fulfilled the octet rule. They have a charge attraction, that +2 -2, that's very strong. When we see ionic compounds, we model this as a transfer of electrons from the metal to the nonmetal, and that's why ionic compounds are usually composed of things that are far apart on the periodic table. So if it's in the upper right-hand corner and the far left, it's probably an ionic compound, a metal with a nonmetal. Ionic compounds are composed of charged particles, ions, that are held together by that charge attraction, by ionic bonds, which are held together by that electrostatic attraction, that Coulomb force. When we write ionic compounds in reactions, we use the smallest neutral subunit. We use a formula unit, sometimes abbreviated FU in these worksheets. So it's like we're just going to look at one of them, the smallest neutral subunit, NaCl. But we have to know that this is actually an extended lattice array. So those ions will be surrounded by nearest neighbors of opposite charge, and that stabilizes those ionic charges. For something like magnesium oxide, that +2 -2, that's a very strong attraction between them, and it gives ionic compounds very high melting points. So we just came out of the heat and energy chapter, where we saw that the energy at a given temperature has to be enough energy to break the attractions between particles in order for something to change phase, to melt or to boil. So when we say that sodium chloride has a very high melting point, we're saying it takes a lot of energy to pull the sodium and the chloride away from each other. All right, so identifying what kind of compound we're looking at. If we have an ionic compound, we're usually going to have a metal with a nonmetal. And when we look closer at ionic compounds, we will see there's also polyatomic anions. Those are charged particles that have more than one atom inside, so they act as a group. And here's an example of one right here. Ammonium hydroxide. That has 2 polyatomic ions, so it looks like it's nonmetals with nonmetals, but it's actually an NH4 plus ammonium ion connected to a hydroxide OH- with an ionic interaction. So an ionic compound could be a metal with a nonmetal, or it could be ions in a charge attraction. A molecule is a compound that has only nonmetal atoms. So it's nonmetals with nonmetals, and those are held together with covalent bonds. And so we're going to characterize more about covalent bonds. There's more to talk about there. Another thing that's different between ionic compounds and molecules is that molecules have a clear boundary. They do not have that extended lattice array. Covalent bonds involve the sharing of electrons, whereas ionic bonds, there was a transfer. It was win-win. They both wanted the electron. The sodium wanted to give up the electron, and the chlorine wanted to get the electron. So it was a win-win situation for both to just exchange that electron. However, when we're looking at covalent bonding, both of the atoms want the electrons, and so they have to share. If we have the same exact atom, like an H2 molecule or something like that, H2 or Cl2, they both want the electrons the same amount. So that will be a completely shared pair of electrons in between them. And that's what we will talk about as a pure covalent bond. Nonpolar, pure covalent, equally shared electrons. I like to show this clear boundary. So here we see HCl. You can see this boundary around it. Similarly with the water, it has a clear shape. So we can talk explicitly about the shape of molecules, and that is where our work lies in Chapter 5, learning to draw and predict the shapes of molecules. There's a clear boundary around it, and that is different from ionic compounds, which have an extended lattice array. So let's take a look at the simplest bonds, and again, looking at hydrogen, H2. On this energy axis, over here, we're looking at the internuclear distance. So these ones are not interacting. At a really big distance, they're just the atoms by themselves. Those are the spherical electron densities, those s orbitals, that H atom. Each of those has a spherical s electron. Now, as they start to come together, you can see that that electron cloud is starting to deform. They're starting to pull towards each other. And when they do that, there is a stabilization that occurs. So now we're tracking down this line. The energy goes down as they get closer together. They get closer and closer together, and they form an increased density in between the nuclei, and that is what we will define as our bonding electron density. And at some point, they reach the most stable position, the lowest energy position, and that's what we call the bond energy. And then as they get closer and closer, if they get too close, that energy is going to go way up. Now, they cannot occupy the same space, so we see an asymptote. They're never going to reach that position where they take up the same space. The energy goes up very rapidly. So we see the usual range of bond energy in this area. And I'm going to draw these lines in. These are vibrational energy levels. So when you look at this lower one, let's talk about the bond length here. The hydrogen is not actually sitting still. It's actually vibrating gently around that distance. So when you're over on this side, the H's are a little farther apart, and then they come closer together. So there's a gentle vibration back and forth around that optimum bond length, that distance. Now, if something happened, maybe it got hit by another molecule or some light or electricity, and it excites that vibration. So now those hydrogens are coming farther apart, and then they're coming closer together. So now they have a more excited vibration. It's a bigger amplitude, going really close and really far. If you add it with enough energy, they can actually completely separate. So if you look at that energy there, that would be the energy to break the bond energy. Now, that bond is a stabilization. So it stabilizes, it reduces the energy. It's a negative energy. So the way that we think about this most accurately with our language would be to say, this is the energy required. We have to put this energy into the system. This is the energy required to break the bond. So if our hydrogen is sitting down at this lower energy level, and then we add that much energy to it, that would be enough to bring it over to this side where the bond would be broken. So this is a reaction profile or an energy diagram or a reaction diagram, and we'll be seeing these throughout the quarter. All right, so let's use our Lewis structures or electron dot structures to represent this interaction. We have our neutral atom with one electron and another neutral atom with one electron, and they get together and they form a bond. So we can write it like this. Now each hydrogen gets access to 2 electrons. So each hydrogen gets to look like helium. 2 electrons becomes isoelectronic with helium. A lot of times we'll write this with a line like that, where that line represents 2 electrons. Now we might think about this as those 2 spherical orbitals coming together and think about that increased overlapping between them, which is a good model. That's a good way to think about it. But there's actually more than that. The electron density actually changes shape, and it is increased in between the nuclei. So it shifts the electron density in between the nuclei, and that is what we were referring to with a covalent bond. In this case, it's perfectly symmetric. The hydrogens both want the electrons equally. So they're shared equally, and we get to double count that electron. That way each hydrogen independently experiences the full duet rule because n equals 1 just has 2 electrons. Okay, let's take a look at hydrogen with a fluorine atom. All right, these guys come together. We can draw those electrons in between them as paired, so this is our dot structure. But a lot of times we'll see that written as a line as well. So again, maybe it would look like this overlap area in between them. One thing is different though, that hydrogen is n equals 1, so it's smaller. And fluorine is n equals 2, so it's a bit bigger. It's not the best ideal overlap. And in fact, what we see in the electron density is that it is not equally shared. There's more electron density around fluorine, which means the electron spends more of its time around fluorine. So we need a way to characterize this tendency of the atom to hog the electron, to steal more time with that electron. And that is the electronegativity. So we'll take a look at electronegativity. What this does is give us an uneven sharing. Fluorine gets more time with the electron than hydrogen, and therefore we have a separation of charge that leads to a bond dipole. So it's an unequal sharing of electrons in a polar covalent bond. We can also see double bonds and triple bonds, and those are represented, again, each line is 2 electrons. So in the double bond right here, we're actually looking at 4 electrons between that carbon and oxygen. So that is a shorter, stronger interaction. And when we think about that triple bond, that is 6 electrons, 3 pairs of electrons between the 2 atoms. Those are even shorter and stronger. So we'll see those when we draw our molecules. Be ready for that. So let's get back to electronegativity and bond polarity. Electronegativity is the ability of an atom in a bond to attract the shared electrons to itself. This is a pairwise interaction, so you're always comparing 2 atoms, just one bond between 2 atoms. The trend for electronegativity increases to the upper right part of the table. Fluorine is the most electronegative atom, and electronegativity increases toward fluorine. You'll see that it increases really rapidly in that upper corner, and it decreases pretty rapidly as well in that upper corner on the right. Notice that the metals, though, these guys are relatively close. There's not a huge change as you go from one to the next. So we can think about electronegativity in terms of how far away is the element from fluorine. And we would consider that one box in one direction is just one step and then another step down, right? So no diagonal. The diagonals are all 2 steps away. We would say that sulfur is like 2 steps away from fluorine, and nitrogen is 2 steps away from fluorine. So we'll be using that trend, that proximity, to see. Another thing to notice is in the top row, they go down by 0.5 on that top row, and that's pretty important, pretty easy to see. Also notice hydrogen. Where's hydrogen? Hydrogen is that element. It kind of runs with the jocks, but it kind of runs with the nerds too. So with electronegativity, it's like it lives in between boron and carbon in the top row with its value of 2.1. So the polarity of a chemical bond or a covalent bond depends on the two atoms involved in the bond. It depends on the difference in electronegativity. So the bigger the difference, the more polar the bond. And we can even think about it as ionic character. An ionic bond donates its electron, the metal donates its electron to the non-metal. We will use electronegativity to predict the type of bond. If we have two elements that have equal electronegativity, then we will say it is a non-polar covalent bond or a pure covalent bond. If there is a difference in electronegativity, then we are going to call it a polar covalent bond, and we're going to indicate that dipole because it has a positive end and a negative end. And that represents that the electrons spend more time near the more electronegative atom. With HF, we can write our notation with a lowercase delta, Greek delta. So it's like a, kind of like that, delta plus, delta minus. It's a lowercase d in Greek. Now, the partial negative is going to be on fluorine because it has an electronegativity of 4.0 and hydrogen is 2.1. So that's a pretty big difference in electronegativity. The arrow is going to go from the positive to the negative and we'll always cross that end to show that it's a dipole arrow. It's not just any old arrow, it's a dipole arrow. So if the electrons spend more time on one of the atoms because it's more electronegative, then it's going to have a partial negative charge, and we'll mark that with a delta minus. If the electrons spend less time around the atom, then it will be the delta plus. It will have a partial positive charge. So we have this axis of bonding from nonpolar covalent bonds to polar covalent bonds to ionic bonds. And notice here that this whole region here is basically ionic. And let's take a look at sodium chloride. I think that was our typical molecule. So sodium is 0.9 and chlorine is 3. So that is a pretty big dipole towards chlorine. And that comes out at 2.1 right here. Right? So there's our typical ionic compound, and it's kind of in the middle of that scale. We're also going to identify the other extreme down on this end. We're going to say that anything with a difference less than 0.4 is nonpolar or pure covalent. That includes the carbon-hydrogen bond. So carbon has a value of 2.5, hydrogen has a value of 2.1, and when we see hydrocarbons in nature, all of the compounds that they form with just carbon and hydrogen are nonpolar. So this makes a very sensible definition to say this is our last nonpolar bond. That bond dipole is so small that it barely contributes. And the way that they form in molecules, they actually cancel out completely. So it's a very convenient definition. And that leaves us with this intermediate range right here. From this section, these are the polar covalent bonds, and they show a separation of charge, partial separation of charge, a bond dipole on that bond. So let's use that notation to indicate both the delta notation and the dipole arrow on the following bonds. So these are not molecules, these are bonds within molecules. Bond polarity is going to be a pairwise interaction between atoms. So we'll just look at the electronegativity, or you could even think about how far is it from fluorine. Carbon is 1, 2, 3 boxes away. Chlorine is 1. This is going to have a dipole, partial negative on chlorine, partial positive on carbon, and that dipole would look like that. Nitrogen, anything with fluorine, fluorine is going to get that bond dipole. What about H and B? Those are really close to each other. If you think of hydrogen as in the top row, but between boron and carbon, they're very close. So this one we might need to actually look up the values. And those were 2.1 and 2.0. So this will say it's nonpolar. We are not going to draw a separation of charge on that bond. The electronegativities are too close. They both want the electrons equally. All right, and then oxygen and hydrogen. Oxygen is more electronegative, so it is going to hog those electrons and spend more time with them. So we will spend most of our time looking at bonds and considering their properties on this axis of bonding from ionic to covalent. We'll just briefly touch on metallic bonding. They have a completely different type of bonding that leads to metallic properties. And so we think of it as a sea of electrons. These electrons are delocalized. They're not committed to just one nucleus. As long as there are enough electrons, then the metal's fine. The atoms can share it. So that leads to metallic properties like if you hit the metal, it doesn't fracture. It doesn't kick off those atoms. It just deforms out of shape. It just lets the electrons rearrange, lets those atoms move. Similarly, there's all these electrons in there, and if you add an electron on one side, let's say you add an electron here, that electron does not have to move through the whole wire to conduct electricity. It just dumps out an electron on the other end. So it doesn't matter. It's not that one individual. It's just the total amount. Like water, if you put one in over here, some's going to spill out on the other side. So metallic bonding occurs between metals. And that's pretty much all we need to know. You can think of it as a sea of electrons. Let's put all of this together and categorize these bonds. Example HF, there's only one bond in the whole molecule, but if we look at something that has multiple bonds, it will just be looking at one bond. It's a pairwise interaction. So let's take a look at HF. This is a nonmetal with a nonmetal. You might want to pause the video and do all of these and then see if you got them right. Okay, HF, nonmetal with nonmetal. That is going to give us, oh, they have different electronegativities. So that's going to give me a polar covalent. F2 have exactly the same electronegativity. So those will be nonpolar covalent. K2, oh, that's a potassium with an oxide. Those are ions. They're far apart on the periodic table. That is an ionic compound. Copper. What kind of bonds are in copper? Copper is a metal. Metallic bonding. Carbon monoxide. There's just one bond in that molecule, and it's a CO bond. C and O are 2 boxes apart in the nonmetals, so those will be polar covalent. Basically, any 2 nonmetals that are not on top of each other will be polar covalent unless they're diagonal in the wrong way. So when we look at nitrogen and sulfur or phosphorus and carbon, we won't be able to use trends for that. We might need to look at the data. All right, oxygen. They both want the electrons the same amount, so that will be nonpolar covalent. Magnesium chloride, that is a metal with a nonmetal, so that one is clearly ionic. And NO, nitrogen and oxygen, Again, there are two nonmetals that are not right on top of each other. These are polar covalent. All right, I'm going to stop there, trying to keep these broken up into smaller groups. So thanks for watching, and I'll see you soon.